Welcome to the Plastek Academy. I'm Donald Preshak, Executive Vice President of Sales and Marketing. Today you're about to view the second webinar in this year's series, as the upcoming presentation will focus on characterization of materials. I'd like to take a moment to reflect on how concepts, relationships, and character build upon themselves. When developing the Plastek Academy program, it was important to us all here to provide a network encouraging trusted and mutually beneficial relationships. Plastek's relationship with Beaumont Industries reaches back more than 30 years with John Beaumont and Penn State Behrend. Relationship and character are why we chose to invite Beaumont Technologies and the AIM Institute to present you with today's webinar, introducing material characterization, how the variation in PCR can affect workflow simulation. I'll now turn it over to our friends and experts and partners, Beaumont Industries and AIM.
Good morning, everyone. Thanks, Donald, for the presentation there. My name is Jacob Trott. I'm the Materials Lab Manager here at Beaumont Advanced Processing for our Moldflow Material Characterization. And here with me is Jen Schmidt, our Senior Instructor for Moldflow at the American Injection Molding Institute. So today, as Donald mentioned, we're going to talk about the material characterization side of things and how that variation in PCR can affect Moldflow simulation. So we're going to get into PCR, what post-consumer recycled material is. We're going to talk a little bit about the Moldflow simulation, what Moldflow simulation is and what Moldflow characterization is. Variations in the material testing that goes into that characterization. Understanding the Moldflow public database and the materials that are listed in there. And lastly, we'll go through some case studies on how these material variations can affect the simulation results. All right, so let's start with post-consumer recycled material, so PCR. A lot of you may be familiar with that, but the image below is just basically easy way to look at how recycled materials for post-consumer recycled materials, their life cycle. So it starts off with virgin material that is processed into goods, distributed to customers, and if it either ends up in the landfill stream or in this case the recycle stream. It goes back, gets reprocessed, repurposed into material that can be used to remanufacture more goods. But the hard part about PCR is it introduces a level of variation that we just need to be prepared for. The stream, the PCR stream, is comprised of, and in this case we're going to look at polypropylene for this study, but it's comprised of anything marked polypropylene on the recycle codes. So comprised of hundreds of different grades from different industries, using all various grades of polypropylene into one stream. And what is that stream comprised of? So going on from there, also what happens when you reprocess a material? So when reprocessing a thermoplastic material, the graph on the left is just a relative average molecular weight versus thermocycles for polypropylene. Every time on a thermoplastic material, every time you thermally cycle these materials, they lose some degree of molecular weight. Now, that can be very minimal in most cases, but as it gets recycled more and more, you can start to see that the molecular weight will start to drop off. And molecular weight is essentially how long those plastic chains are. So that also changes your molecular weight distribution, how many long chains versus short chains you have in your overall material. So the thing about molecular weight is molecular weight drives properties of materials. So as you lose molecular weight, you start to lose properties, mechanical properties, physical properties, thermal properties, etc. So what is this stream comprised of when this is included in your material? And how do these manufacturers of these materials meet specifications? I have two examples of notes listed on a data sheet for a PCR material that are pretty important to kind of understand. The first note may contain equal to or greater than 20% PCR. So that's essentially saying the 20 to 100% of the material could be PCR. So they can use as much PCR as necessary along with their virgin material to stay within their specifications. And furthermore, if you're familiar with an MFR or a melt flow rate testing, the specific material I pulled off was a 15 to 30 grams per 10 minutes. And melt flow rate testing can be used to understand and compare average molecular weight of your similar materials. And in this case, you can see that 15 to 30 is fairly wide spec. So these materials are meeting spec. They're within tolerance, but they are fairly wide spec. So you can be prepared from lot to lot to see a fair amount of variation. So then we get into what is Moldflow simulation. So Moldflow simulation is a software that simulates the injection molding process, going from fill, pack, and the subsequent shrink and warpage that you see on a plastic part. So what is this often used for? It's often used in part design and mold design to help define and investigate part defects and generally call out processing concerns when you're trying to simulate the process of a material or of a sample. In this case, we're going to focus on 3 polypropylenes as we discuss material characterization. 3 polypropylenes that range from a fractional melt, so a very high viscosity polypropylene, up to a very high flow or very low viscosity polypropylene, and 1 material that's in between the 2. So on the material characterization side of things from Moldflow, we test several different lab tests of the material properties to try to understand and input into the software how this material is going to behave. So we look at rheological properties, thermal properties, PVT or pressure volume temperature relationships, and mechanical properties. And as we go through these 3 different materials, the fractional melt to high flow, these different things that the stream could be comprised of could be the difference in molding the same part that you see on the right and getting those 2 different amounts of fill at the same pressure. So huge variations in materials, creating many variations in the process downstream. So what is the stream comprised of? So we're going to go through the material characterization, those few bullet points about the rheological, thermal, PVT, and mechanical properties and how that may affect and the variation can be seen from PCR into simulation. So the first thing we're going to talk about is rheological properties. We have the 3 polypropylenes that I mentioned listed on this viscosity versus shear rate curve. As you can see, there's 3 blurred lines essentially. Each one of those 3 lines is actually the same material tested 4 different temperatures. So as you can see, these 3 different materials that we have listed, even at different temperatures, they behave very dissimilar to one another when we talk about a rheological aspect. Viscosity itself, well, what's that going to affect? Well, as you change in viscosity, that's going to affect the flow behavior of the material, which downstream that's going to affect the pressure required to fill the part and the internal stresses that are generated within that part, which we'll get to later on. Then we have thermal properties. So on the left side, we have thermal conductivity, and on the right side, we have specific heat. As you can see, there's only 2 curves on each one of those. That is one thing we'll talk about when we get into the material files. But if you notice on the very edge of each curve, there is a blue dot. So in this case, this material was, there's 2 materials that are well characterized or fully characterized, and this third material has single point data or very minimal data sets used. So in the thermocomic conductivity, you can see that they behave fairly dissimilarly, just like on the specific heat curve on the right. However, on the specific heat curve on the right, we do all these tests through cooling, and as you can see, as it cools, we find this spike. This spike is the transition or the crystalline transition. So this is where materials, in this case polypropylene, are readily and rapidly crystallizing. And just knowing that, we can see that these materials are behaving differently in the crystallization realm. And the material behaves differently on level or amount of crystals. That's going to affect your shrinkage, subsequent warpage, etc. So these materials do behave differently. And the important thing for the simulation is that thermal conductivity has an inverse relationship with specific heat, which describes the thermal diffusivity equation. And this is basically how the simulation will know how and the rate at which these materials are storing heat energy and transferring heat energy. Then we go into PVT, or pressure volume temperature relationship. You can see on the y-axis we have specific volume, and on the x-axis we have temperature. The individual lines you see on the graph are isobars, or they are the pressure for these three different materials. In this case, we're looking at a zero pressure on the specific volume versus temperature graph scale here. So what's this describing? This is describing how the material is going to volumetrically shrink as it cools. So as it goes from a higher processing temperature down, we see how this material is volumetrically shrinking, in which case we see a rapid change, which is where the material is crystallizing, and continually shrinking down to room temperature. So specific volume, also the inverse of that is density. So this plot at any given pressure and temperature gives the simulation the idea of what the volume and density is of the material as it goes from a molten part and cools. So differences in shrinkage in different areas of your part ultimately is going to equal into warpage. So differential shrinkage equals warpage. So this is why the PVT relationship can be so important. And then lastly, we're going to talk briefly about mechanical properties. So on the left, you see a stress strain curve of the three materials. Stress strain curve is just your simple your tensile test, pulling a dog bone, however you may recognize that. As you can see, they behave fairly differently. We're going to talk specifically about modulus and Poisson's ratio, modulus being the stiffness of the material, which is grasped from the beginning of that, the linear region of those curves. So as you can see in the picture on the right, this can mean the difference between a material that is sticking straight out, so that material is a higher modulus, it's stiffer, it can hold its own weight, versus the material closer that is falling down from its own weight is a lower modulus, less stiff material. And lastly, we also have Poisson's ratio that is used, which Poisson's ratio essentially describes compressibility. And a tangible way to understand this is pulling a rubber band. As you pull a rubber band axially, in the other directions, it thins out. So that's showing the compressibility of the material, which is incompressible for most rubbers. Ultimately, as we go through this, and as this material is shrinking and does have any differential shrinkage, if it doesn't have the mechanical ability to resist those internal stresses that are being created, well, then you end up like a part that you see on the bottom of the screen, you end up with warp. And the degree of warp can be much different between all these different polypropylene materials based on this idea of differential shrinkage and the relationship with mechanical properties. So then part defects. So let's go into a little bit about how this material characterization is going to, and the variations included, are going to affect the part overall. Well, we know the rheological properties, the viscosity properties of the material are going to affect fill pressures. But how is that going to affect simulation? Well, that's going to affect what you're simulating your machine capability is, the available pressure you have and how much you're going to need when you simulate it, the clamp tonnage requirements, the internal stresses that are generated. All of those things can be variables changing as we change these different materials, which are changing in rheological properties. When we talk about thermal properties, we're going to change our cooling profile. So as we have differential thermal properties in these different polypropylene materials, we're talking about different frozen layer development simulation, which is going to affect with the flow behavior of the rheological properties, the fill pressures we see. And ultimately, if we have differential cooling in different areas of the part, that's going to lead to differential shrinkage and overall warpage. We have the pressure volume temperature, the PVT relationship, so that we know that's describing how it's going to volumetrically shrink. Is the material going to sink or void, and how aggressively? And again, differential shrinkage equals warpage. And lastly, with our mechanical properties, we know that's going to have its main effect on warpage. So are the internal stresses that are generated, does the material have the modulus or the stiffness to resist those internal stresses and warp? And to what magnitude will this occur? And lastly, we also test in that mechanical property set thermal expansion. And is this thermal expansion contraction, the differences in that going to affect further warpage? So now think of all these different properties, all these different variables that are changing, the process outputs that are changing based on the material changing. Now imagine we have a significant viscosity shift and how all of those aspects are going to change. Our fill pressures, our machine capabilities, how the part is going to cool and shrink and warp. So how can we mitigate this? Well, we can predict this by trying to set up a very robust process, but also one thing we can do is try to keep retains of different lots of materials. And as you start to get a feel for the stream that's coming in, the material that you're ordering and the variation in that stream of PCR, maybe we have a low spec and a high spec material. We have a material with a very low viscosity and a material with a very high viscosity. And you can test both of those materials and look at it and actually simulate multiple simulations of different materials you've actually physically processed to see the variation just seen from those two lots you've actually had in your shop. So that being said, we understand the variation a little bit. Let's go into the Moldflow database, understand the public database. So within Moldflow, there's thousands of materials that you can pick from in there that are already pre-programmed in the software without even getting material characterized. There's a few different things you can look at. So when you open up a UDP file or the material file that's in Moldflow, this is the first description tab that you're going to see pop up. There are a few key pieces of information you can get from that is you can understand where it was tested and how, and also the data was tested or modified, in which that can be pretty important because, as you know, as the material card ages, there's a good chance that material may have changed raw material suppliers, may have changed the OEM overall. Something along that supply chain to create that material could have changed, and it may be worthwhile to have it retested or characterized to understand the behavior changes that you're going to see in the simulation and on the shop floor. And then up in the right-hand corner, we see a tab called the Material Data Completeness. These are the Material Data Completeness indicators. And what they are is they're a gold through bronze rating that many people are familiar with that work with Moldflow that give you an idea of not the quality of the testing that was done, but on how thorough it was tested. In this case, you can see in the material file, we have filling, packing, and warpage indicators. And in this case, they're all gold, meaning that if we open up each one of these view details tabs, we can actually see that there's a bunch of radio tabs that describe how the material was tested, the method used, how recent it was tested, and if it's multi-point data. All of these things are going into this rating scale to give you an idea if this material was thoroughly tested by a lab testing for these variables, or if it was single point data or textbook data that was just input as a generic property set. And we have these tabs for each one of these ratings. Another thing to look out for when you have material cards in Moldflow is if you see any of this red text is supplemental data. And it's important to note that that comes from family generic data or textbook data that describes, say, on average, this is what polypropylene does. But as we know, polypropylenes have quite the range of properties that you can see based on their composition. And lastly, when you go into the material file and any of the tabs, in this case, Rheological Properties, we can go in and we can open up the Rheological Properties, and every single one of these tabs has an edit test information, in which case we can open that up, look at the data source, who tested it, when it was modified or tested, and the method that was used, and any comments associated with that. So it's always good we can dig deep and see how this material was tested before we even use it. And with that being said, I'm going to pass it over to Jen Schmidt, who's going to go a little bit more into the material indicators, and then she's going to go into some case studies on how this all affects simulation downstream.
All right, thanks, Jake. So Jake covered these material indicators pretty well. They vary from gold, silver, and bronze. And we kind of went over the way they get graded. It's, you know, who tested it, the quality of the material, multi-point, single point. But as you said, it does give the analyst kind of an indication of how much I can trust that, how much stock I'm going to put in my actual results. Bronze, I always say, is the bare minimum to get it in the database. It does tend to be a lot of single point, a lot of supplemental data, but it should still give us information on trending, help us pick gate locations. If you're looking for exact warpage numbers, you really need a gold-rated material. In Moldflow, there is roughly 11,500 materials in the public database. And for a simulation program, that's a good number of materials. But for real life, I mean, there's a lot more materials out there than that. And within that database, there is some recycled content in there, but it is a very small percentage, at least in the public database. There may be more available outside of that, right? Sometimes people keep this private. So I want to start with just showing the variability among material characterizations, right? So this is 6 different grades, or sorry, 6 different characterizations of the exact same grade of polycarbonate. And they were tested by different sources, by different methods. There's gold-rated materials in here, there's bronze-rated, and kind of everything in between. For this particular bar graph, the part mesh is identical, and the type of mesh and the density. I will show a variation in a later slide, but we don't have time to get into all the details about simulation. But the analyst can choose different mesh types and how fine of a mesh they put on it, and all of that is going to affect our accuracy. So again, 6 different versions of the same exact grade, run at the same processing conditions. The only change I've made here is you'll see a blue and orange bar. One is meshed with beam as runner systems, which are simple, quick, easy. One is meshed with 3D tetrahedrals. The big takeaway is they use different solvers, so you will get different answers between them, right? And you can see there's a wide variation in pressure predictions on this. I think the easiest thing would be to take the min and the max and compare that. And so the highest pressure prediction I saw in here was just over 26,000 PSI. The lowest I got was 10,000 PSI. Again, for seemingly the same material, same process setup. And I always say I'm not trying to scare anyone with this data, but maybe it should be a little bit scary, right? Because that is a 16,000 PSI pressure difference when in theory I'm running the same thing. Now, if you're curious, because I would be, the 26,000 and change was a gold-rated material. It had been tested within the year prior, and it was fully characterized to our MPL 150 test. The 10,000 and change pressure prediction was a bronze-rated material with a lot of supplemental single-point data. I am going to put a lot more stock in the gold-rated material. Now, this example, I am now just looking at mesh types. So I'm taking one material characterization. It's that PC number 5 from the bar chart because that was the gold-rated material fully characterized. And I'm running it all at the same processing conditions again. And the only thing I'm varying here is the mesh type. So I have a 3D part mesh and a beam runner system, a dual domain part mesh and a beam runner system, and a 3D part mesh with a 3D runner system. And even within this same material card, I'm getting roughly 7,500 PSI difference. And really that's just kind of showing you the solver differences, right? Now this is polycarbonate, so it might be exaggerating it a bit more than if we looked at polypropylene, but there is variation just in the characterization. Now, $1 million question that people always want to ask me, how's that compare to real life, right? And so I'm not going to sit here and tell you one mesh type is always more accurate than another mesh type. This stuff can be very case by case dependent, and there's very good reasons to change mesh types. But for this particular part, I am going to pick the 3D part and the 3D runner system. It also doesn't hurt that this is the highest pressure that I saw, so therefore the most conservative, right? So I got 26,000 and some change. This is an 8-cavity tool. We're representing them with occurrence numbers within the software, which is a common way to do this. The beauty of this tool is we have this internally. It has a lot of sensors in it, and I can get my colleague to run it on the shop floor. And what he got for a transfer pressure was 35,388. And on the surface, that may not look like I or the simulation did a good job. But what you have to remember is the simulation is only going to predict what I've modeled. And what I have not modeled that my colleague will see is the machine nozzle. So we will have pressure losses through the machine. We'll have screw conveyance losses that we need to account for. You can do that on the shop floor by grabbing an air shot, and that's just about 8,000 PSI. And when we subtract that off, that is a fair pressure to now compare to the simulation. Now, this still isn't exact, but honestly, for simulation, this is pretty decent. It's within 5%. There are more reasons that this can be off that I just don't have the time to get into today. But I always tell people, you can see our website at AIM. We tend to do tech articles and webinars about mold flow versus mold floor. So let's look at the 3 polypropylenes Jake had referenced, right? So I have my low melt, my medium melt, my high MFI, and you see quite a variation in pressure across that, right? And this is a pretty simple part. You could imagine if we took a more complex part or a different material, we might see more or less variation. I also want to look at deflection. And again, this is more than a factor of 2 that we're seeing here. Simple part again, but just kind of illustrate the point of variation. Now, that was the difference between a 0.6 MFI and a 53 MFI, which is a pretty wide range, right? So I'm going to go back to the same data sheet I think Jake had referenced and look at something that's a little bit more common of recycled content. And typically you do get a range of MFI. And so this particular one is showing us that range of 15 to 30. Again, I don't have a ton of options for recycled content currently in the database, or not, at least not in the public database. So what I did was I took 8 examples of an impact copolymer polypropylene, and they all have MFIs between 15 and 30. And we're looking at some of that same data that Jake had provided before, but on these 8 materials. So you're seeing viscosity curves, PVT curves, and then that thermal data. On that thermal data, real quick, what I'd like to show is how Moldflow gets the transition temperature in here is this intersection between these 2 curves. And if you see where all these peaks are, you're getting different intersections. So Moldflow considers the transition temperature, anything above that temperature, it considers it molten. Anything below it, it considers it solidified. Where that's important to me as an analyst is that's how we determine gate freeze. So you can imagine I'm going to get a wide range of gate freezes in theory on the same source material, right? Depending on which one of these ones I would choose. So I'm going to run that through that same geometry you saw before. I'll show it to you on the next slide. It's just a simple lid geometry, just one cavity. But again, just to illustrate the variation through these 8 different polypropylenes. And you can see, interesting enough, it doesn't necessarily trend with MFI, right? This 15 to 30 melt, this is one of the highest pressures at the highest MFI, which in theory would be a lower viscosity material. And that is a trend that I do see often. But you do see the variation. So what I'm showing here is just the 2 highest and the 2 lowest to kind of show the extremes, right? And you'll see between them, we have nearly a 2 times pressure difference between them. And again, one cavity, simple geometry. Imagine if we applied this to, a 48 cavity or 64 cavity with more interesting geometry or more difficult geometry. So just the potential for variation. The other thing I'm going to show is deflection, because in my world, those are normally the 2 big things people care about is pressure and warpage. And so what I'm showing on this chart is flatness of the bottom of that lid. So this is the total delta on that flatness. And again, not necessarily any trend with this, right? And so same as before, let's look at the 4 extremes. So the 2 highest predictions, the 2 lowest predictions. Ironically, these are not necessarily the same 4 we looked at last time, but in here, now we see more than 2 times off, right? So again, just a wide variation based on what material we're looking at. Now, the last thing I did with this is I imposed those two sets of data just out of curiosity, and there's really not a discernible trend between the two. But I just trying to highlight some of the variation here. So I think in summary, there is inherent variability with the simulation program that I don't even have the time to necessarily get into, right? But there's different brands of this software. There's different levels. Sometimes there's a high-end level and a lower-end level that's easier to use. You get it quicker up front in your process. There's different types of mesh. Moldflow has 3 different types of mesh, and you're relying on your analyst to know when to use what one. Mesh density, right? How fine of a mesh I put on it. These are all analyst decisions that have the ability to affect the accuracy at the end. What was modeled? So if I only model the part, do I model the feed system? Do I also take into account the cooling? That's going to affect our warpage values. What was actually cut in steel? Process settings. I always say I'm trying to guesstimate the process settings up front, but I don't have the same buttons, nor do I get the same feedback that a process engineer will get. So there's variation between mold flow and mold floor. Moisture content's another one that I thought we could bring up real quick. In Moldflow, the material's dry, right? I have no ability in the simulation to adjust the moisture content, where in real life, that is going to affect your viscosity, pressures, etc. Obviously, we've been talking about material characterization, and there's many other reasons just in the simulation. Now, add to that any variation in your material sourcing, right? So all different kinds of polypropylene, different grades, how many times it's been reground for all the reasons Jake talked about. And he did mention this, but I'm going to finish on this because I think with all this variation, it can be very hard to get distinct, accurate results in Moldflow. And so if that's what you're looking for with recycled content, I think the best way to go about it is to take a high-end and a low-end version of maybe what you typically see as a lot of recycled content, characterize both those, and then you could run that through simulation. That should at least give us a representative range of what we might expect to see for simulation results. And with that, I will turn it over to Nicole.
Hi, everyone. My name is Nicole Freeman, Marketing Coordinator here for the Plastek Group and moderator for this webinar series. While I am the final face that you'll be introduced to today, you are the first thank you I want to put out today. So to our audience, I thank you for attending this webinar and hearing from our experts, Jake and Jen. So my second thank you goes out to you guys. On behalf of us all, I think I can say that we value the feedback that these trial and errors can provide to us and appreciate the time that you, your colleagues, and your facilities invest in providing this information for the plastics industry. Audience members, to wrap up this webinar today, we have 2 final brief sections for you, starting with the traditional Q&A session. So as you are hanging on with us, please utilize your dashboard at this time to submit any questions that we can ask Jen and Jake on their topics that they presented today. We'll give you a moment to do so, and I will also reference a few secondary opportunities that we have for you. I can tell by Jen's comments that there's so much more that she is excited to share in her field, and I'm sure Jake as well, as we view this as an introduction to material characterization and mold flow simulation. So to help aid that time frame that we have today, you will see on your dashboard 2 PDF handouts that Beaumont Industries and Technologies and AIM Institute has provided for you. So one of them being a flyer that looks like this for their tests and a little bit more description of services they can offer, as well as some classes and training that you can utilize for your personal development and within your organization. So if you are at all interested in learning more about those opportunities, please take a moment during, after the questions, before you click that X button out of the webinar today, to click on those PDFs so that they are open for you to download and save for a later date. As we get started with some questions here, we will open the floor to our first question. Jake and Jen, we would like to know, how do you know what level the material used in Moldflow was characterized to?
So in the simulation program, there's a studies task pane, and there's tiny little icons that give me a very quick reference, whether it's gold, silver, or bronze. But I think the better way is to go into the material details, which is some of the pages Jake had shown, and then you can click in that material data indicators, and it will tell you, his example was gold, gold, gold. But it would tell you the different classifications. In warpage, the gold is somewhat mesh dependent. So I always tell people gold may not be enough depending on how it got to be gold and what mesh type you're using. So I think it's good for the analyst to go in and dig into that a little bit more.
Okay. All right, we have several questions from our audience today. Thank you for your engagement. I'm just going to go down the list with the next question. Does observations of high and low MFR, let's see, scroll back up here, characterizations true for all material families?
Yeah, so obviously we can see this with any material family, and as Jen mentioned, it may be worse with different material families than others. Oftentimes amorphous materials like polycarbonate, when you see these differences, can have more of an effect on the material properties and therefore the simulation results. But in all families, all families of material, any changes in MFR, we can't use that as a generic way to look at it, but MFR within the same material family, that's an overview of a comparison of a general average molecular weight between them. And like I said, as you change molecular weight, you change properties, which are going to change your simulation results.
Okay. All right, the next question coming in is, in the PC example you referenced, did PCS and P6 have D3 data? We've seen D3 data really bump pressure on PC simulation.
So that is a really good question. Also might be a can of worms to open in a Q&A to get into D3, which is pressure dependence on viscosity. PC number 5 was the one that was fully characterized, although PC number 6 I feel was too. I know they were gold across the board to MPL 150. I don't believe they had D3 data, which, yes, does help to bump up the pressures in applications that need it. I could go into more detail about when you need to use it, but maybe that should be saved for a future topic or we'll run out of time. I can always double check, but my gut feel is no, those ones didn't have D3. But outside of the pressure, that part didn't necessarily need D3. It was the high pressure would kind of require it. But we got pretty good correlation even without.
Sure. Thanks for attempting that today, Jen. So speaking of data being available, we do have a question in regards to the database. If a material isn't available in the database, what is the typical lead time to get material characterized at gold, silver, or the bronze level?
Sure. If you need a material characterized, the first thing I'd like to throw out there is it's always good to refer back to your manufacturer, the OEM of the material first, to see if they have a file or if they're in the process of getting it characterized. However, if you do need to get a material characterized, it takes roughly about 4 weeks from the time of the material arriving in our labs to get all the lab testing done in a large report and a material file that's ready to be input right into Moldflow and used.
All right, thank you. We have a couple minutes left. Let me scroll through these and see if we can get something with some variety here. Lots of thank yous for the presentation again, Jake and Jen. So we'll definitely have some follow-up information here as well. Let's see. Let's go with this one here. Given the variation in material properties with PCR as it is added as a percentage, is there a feature like DOE that can be utilized to try to get more information on how these variations will affect what we are looking for in simulation results?
So there is a DOE analysis or DOE function inside of Moldflow, and you can run it like a DOE on a shop floor, a design of experiments, right? So we can take one variable or multi-variables depending on how intensive you want to run this DOE, and then play around with different processing conditions, or you can even play around with part geometry and thickness to some extent, and then see how that's going to affect the results. Results, it's the way you set it up, it's what you see. So if I replicate more of the injection molding process, I get more of those results. So if you want to see warpage results, we can set it up the whole way through that. Yeah, there is that functionality though inside of Moldflow that could be helpful, absolutely.
Okay. All right, thank you for your answers. We do appreciate them. And again, we appreciate the audience. We have maybe one or two more that were fairly similar that were submitted, and we'll certainly get back to you and help you find those answers for your questions. So I want to wrap up this webinar today with our final slide and continuing your personal development within the plastics industry and our webinar series. So I will open the floor in a moment to Jake and Jen for any final statements that they would like to make on behalf of their organizations. But on behalf of the Plastek Group, again, we thank you and we encourage you to continue following us through our personal development and training as well. I know that we often get questions about the material we presented today being shared with you, and in an ever-progressing efforts of sustainability in the virtual world that we live in, we do encourage you strongly to revisit this webinar. If you'd like to view it again, it will be available on demand through the Plastek Academy website, and you'll also receive a link in an email following the webinar. As well as if you had a colleague or industry member or student that you would like to share this information with, we do encourage you to share the link with them as well. We will also continue learning about PCR, materials, and technology as core highlights within the series throughout the rest of the year. So be sure to check out our upcoming webinars in the following month from the vendor and suppliers listed on the right. Especially highlighting with a new hyperscale sorting and recycling facility coming here to Erie, Pennsylvania that will be presented on next month, as well as automation and mechatronics and market outlooks throughout the rest of the series. Jake and Jen, any final comments?
We'd just like to thank everyone for joining the conversation. Yeah. As you know, PCR's at a level of variation, but it can be managed. It's never a bad thing. We're doing a good thing. It's just we have to be able to understand the variation involved and tackle it.
Yeah, and thank you, Nicole, for the opportunity to speak. So.
Our pleasure. Thank you very much, everyone. You will be prompted with a brief survey as you exit, and don't forget about those handouts. Until then, and next month, have a great day.